Welcome, one and all, to everything I need to know about AIOps I learned from my rice cooker. Now, you might be asking yourself, will a rice cooker feature in this presentation? Yes, it will. Now, I'm a principal developer advocate at Lightstep. You can find me on Twitter at Austin O. Parker. Now, back to Lightstep. If you're not familiar with us, we are an observability and distributed tracing tool that makes it really easy to understand your system. We take telemetry data from all of your different services, from your Istio, from your Envoy, from your app code, and we look at 100% of that data from front-end client to back-end database, and we give you insights. We help you figure out what went wrong when something, a new deployment goes out and things break. You can learn more about us at lightstep.com, play around in our sandbox environment. Now, I'd recommend you give it a look if you're interested. Now, back in the before times when this still happened, right, when we got to go to conferences, one question I got really frequently was, if Lightstep uses AI. And it always took me back a little bit. I don't think anyone's using AI in the way that I imagine it. I mean, if you really think about it for a minute, what is AI? Well, I think we should distinguish between, what AI is and what it really practically is these days. So practically, when people talk about AI these days, what they really most of the time mean is applied machine learning. And that in and of itself is a very broad field. In the DevOps world, Gartner and other companies and researchers and market analysts have kind of come up with this idea of AIOps, right? And it's the application of machine learning and its related disciplines to the problem space of IT operations. And the promise of AIOps is great, right? Gartner has a couple of examples about what this actually means in their reports, but at the core of it, it's pretty simple. It's pretty straightforward. You gather up all of your telemetry data, your operational data from your applications, your infrastructure, your business processes, and then you detect interesting signals within all that data, and then your AI tools will, either automatically remediate and, find the root cause of a problem, or they'll say, oh, I need a human to step in. And this is all well and good, and there's just one problem. There's one thing keeping us from our beautiful robot future, and it's that, by and large, this is all. So, that said, let's get to what we're all really here for, and let's talk about rice cookers. So, I would like to introduce you to Zojirushi. This is a NS ZCC10. This is the premium white model of this rice cooker, and I believe this will do 5 cups of dry rice and give you about 10 cups of cooked rice. It'll do all sorts of rice. This will do white rice, brown rice. I think you could probably do quinoa in here if you really wanted to. When it's done making your rice, it'll play this song that's really catchy. Now, if you're boring, you can just say, no, make it beep. But this is a wonderfully engineered kitchen gadget that will make perfect rice every time, and I love it. Now, you might be asking yourself, how does it do that? What is the secret to perfect rice every time? And I'll show you. It's right here. It's this idea, this neuro-fuzzy microprocessor that is inside, it's contained within these 4 walls. Now, you might be saying, what is neurofuzzy? Well, what it really means is fuzzy logic. And what is fuzzy logic? To simplify, it's kind of a method of dealing with uncertainty. And I think that's actually really important to understand a little bit, how that all works, because it's actually really applicable to how AIOps works and how a lot of things actually wind up working. So let's take a look. Now, let's start out with a brief primer on logic. Classical symbolic logic that you might be familiar with from taking a CS class, holds that there's 2 valid conclusions to any proposition, true or false. In this world of symbolic logic, things can be true or they can be false. And that is something that I think we deal with a lot as technologists, as developers, as IT admins, as DevOps professionals, as SREs, as whatever, right? Like this basic idea of Boolean logic is ingrained in everything we do. My application is up or it's down. I'm an admin user or I'm not. A feature flag is enabled or it's disabled. Simple stuff, right? But life tends to breed levels of uncertainty that are very difficult to completely quantify in this kind of logic. I'll give you an example, and it has to do with age. This is Robert De Niro, and it would be true to say that Robert De Niro is old. This, on the other hand, is Lil Pump, and it would be true to say that Lil Pump is young. However, when you start getting into degrees of old and young, it gets a little more complicated. So, from my perspective, Robert De Niro is old, and Lil Pump is young. However, if I was to change the basis comparison, someone that's closer in age to Robert De Niro, they would say, well, he's not that old, right? And they would then, by extension, say that Lil Pump is very young. Now, if you, again, change the basis here, right, and you say, hey, what does my 10-year-old nephew think? Well, he would say that Lil Pump is old, and that he would wonder who Robert De Niro is because my 10-year-old nephew hasn't seen Raging Bull, the Philistine. Being able to gauge this level of relative truth, it sounds easy to you and me, and it is, but it's very hard for a computer. But that relative truth is actually super important for how a rice cooker works. So let's talk about rice some more. Now, how do you cook rice? Well, rice is actually really straightforward to cook. So in a traditional rice cooker, and also in the Zojirusi, you take rice and you take water and you add them into a bowl, right? I take my rice, I take my water, I close the lid, and I tell it how long do I want things to go for. What's actually happening kind of behind the scenes here is that as water heats, water will heat up to boiling, so 100 degrees Celsius, 212 degrees Fahrenheit or whatever. And at that point, the water cannot get any hotter. It will begin a phase conversion instead to steam. Now, as the amount of water in the container is reduced, that will actually increase the temperature inside. And in a traditional rice cooker, a couple things can happen, or a couple of ways to deal with this. One, it can simply be time-based, right? For X amount of water, Y amount of rice, go this long. Slightly more advanced ones will do some sort of, thermocouple, or a really neat property of magnets, which is certain magnets, when you heat them up to a certain point, will become non-magnetic. And what would happen is, this is going, it's heating, the water is boiled off, it's turned into steam, everything else is being absorbed by the rice, it gets done, boom, and I would have cooked rice. There's a lot of confounding factors here, though, and it sounds like there aren't. But if you think about it, there's a lot of environmental factors that I can't control that go into how quickly things will heat up. For instance, if it's a very hot day outside or a very cold day outside, then the ambient temperature is increased, which will thus increase the rate of the entire bowl becoming warmer. If it's cold, then it would take more time. Now, again, if I take some dry rice and I add some water, I will get cooked rice. But the rice and water here are actually a controlled variable, right? As I said before, white rice or brown rice, white sushi rice versus, normal rice, or even pre-washed rice versus non-pre-washed rice, these are going to affect the cooking time and the temperature. And I have to follow the directions. One thing that actually has gotten me with my rice cooker is that I lost one of the special measuring cups and I had to order new ones, because if you don't use the special measuring cup, you're getting the wrong amount of rice. And so your rice will come out slightly off. So if I don't do it right, either I don't have my measuring cup and I add the wrong amount of rice, I eyeball it, that's going to cause less than great rice. But what if I really go off the reservation, as it were, and I add rocks? And I say, rocks plus water, what's that going to do? Nothing good, right? Like, it's not smart enough to realize that I put rocks in instead of water. Or, I'm sorry, instead of rice. At best, I'm going to get hot, wet rocks, which I can't eat. But for all that fancy technology, for all of my, hey, I've got a microcomputer in here and I've got fuzzy logic, it can't tell that I'm doing something completely wrong. It can't tell that I've gone so far outside of its bounds that, you know, it would never actually work. Now, this has more sort of theory behind it, I guess, than I'm really getting at. There's this law of cybernetics called the law of requisite variety. And what this is saying is that to address the diversity of a given problem set, then you need to have more responses, or at least an equal amount of responses to all possible problems. So if you violate this law, then you could get the correct response from an incorrect input. For example, if we violated the law of requisite variety, then my rock plus water could give me rice, which is obviously a false statement. And it's pretty essential when you think about controlling a system, right? That I need to be able to respond to every possible input, or at least I need more, whatever the range of things that can happen, I need responses plus one. And that plus one might simply be a, hey, I don't know what happened, but I have to have that response. Fundamentally, there's not a lot of difference between the branching logic that my rice cooker employs to, figure out how long to cook rice, and what a outlier detection engine is doing in a, some sort of monitoring tool. Like, it's a bunch of fancy if statements. The difference is that my rice cooker will run me about $120, and a fancy AIOps tool might run you a factor of 10 or 100 more than that. So why is that the case? So AIOps tools have to deal with two real main conundrums. One is this idea of infinite uncertainty. So, maybe it's not infinite, right? But at least it displays asymptotic behavior. Sorry. So if you look at you look at the line here, we've plotted very simple y equals a plus b over x, where x is time, y are unique system states, and then a and b are like users or components. So if you think you can quantify your entire application, your entire IT operation, your entire business process, like as a set of controlled states, then I think you will find that you are lying to yourself or you are lying to your boss. Pick one. The reason why is there's so many variables about a modern IT system. Even simple applications, are abstracting tens or hundreds of thousands of other components that are, if not unknowable, at least very difficult to completely quantify, because a lot of them you don't have ownership over or you didn't build in the first place. And when you start taking this and you kind of radiate out and you think about bigger and bigger concentric circles outside of here's my timekeeping application, or here's my inventory application. If I'm relying on a managed cloud provider for my database, or if I'm running on Kubernetes, then I've added so many more things that I need to be aware of and that have their own kind of complexity fractals that I need to understand. Now, the second thing is that you have infinite outcomes to contend with. And I hope at this point that me putting up the requisite variety chart is going to be unsurprising, because if I have infinite possibilities, infinite cases to handle, and then infinite outcomes to handle, I have a problem, because infinite is a number that I can't reach. This is easy, in a way, right? If I constrain my problem space. Right? Rice cookers manage this, after all. But there's a big difference between a rice cooker and sort of your IT ops. My rice is done or my rice isn't done, right? These are the two possible states of rice. Cooked, uncooked. IT systems, though, work in a slightly different world. Now, I can have a lot of outcomes, and I can have a lot of outcomes within a range of acceptability or unacceptability, right? If I'm using service level objectives to kind of measure this, then I can say, all right, here's my SLO. all requests with a non-500 response, so everything that's not an error, should occur in less than 200 milliseconds, 99% of the time, over the 30-day rolling window. And if I fall out of that, then I'm violating SLO. Now, there's a range of good and bad under this, right? We can simplify and say, okay, anything breaking the SLO is bad. We can say, so everything that's 201 milliseconds plus, bad. Everything under that, good. But we are missing complexity in everything, in that 0 to 200 range, right? What if 80% of it is at 199 milliseconds, right? That's something that maybe we will have wanted to notice over time. And beyond even this, SLOs can change. And I would argue in a lot of ways they should change, right? Because as your software changes, you'll make different trade-offs that should inform how you're planning to do this stuff. The SLO itself might still be good, but how you get there might be bad. Or vice versa, right? Let's talk about this a little more in depth, because these are hard questions. These are hard questions to answer by humans. And I think if you have been part of a large organization, you've probably spent a lot of time trying to answer optimization and trade-off questions. They can take weeks or months, quarters or years to understand. This is, a very small example. This screenshot is of an internal Lightstep system. And I took this shortly after, a couple days after a deployment of a new version. And what you can see is on my error rate has increased immediately after the deployment. Was this good or bad? I don't know, because I didn't go investigate it. We can assume, as human beings looking at this chart, that since the error rate went back down, this was probably fine. This is probably some, resulting change of the deployment happening. We can also see that the error rate had climbed on one side of the old version, so this could be an artifact of a rolling deploy. This could be maybe there was a problem happening and we needed to patch quickly, right? I don't know for certain, but what I do know is that if I gave this data to a machine learning algorithm and I said, hey, alert me on something going wrong and automatically remediate it, it would probably see that deployment, say, oh my god, the error rate is like 3 or 4 times what it usually is, and it's usually 0. Roll back, page someone. That might not be the right answer, right? Also, think about optimization, not even micro optimization, like legitimate optimization. Maybe my team decide, maybe if I'm the service owner on this or any other service, I say, well, we can increase latency but reduce memory utilization by 50% for a 25% increase in storage, in ephemeral storage costs. That's something that could be a valuable trade-off, or it might not be. But I can tell you what can figure that out a lot quicker than a big fancy ML algorithm, and it's called Excel. And the person that's running that copy of Excel can do a lot more than just detect outliers when a graph goes in the wrong direction. I think that what I'm really trying to get at here in a lot of these cases is that we need to be more responsible and more rigorous about how we talk about this, how we think about this, and how we do stuff with ML and AI. So the first thing, my first fix here is stop calling statistical analysis artificial intelligence. Stats are great. I love stats. I'm not good at them. That's why I have a computer. But you can do most of the stuff that's actually happening in an ML or AIOps situation is simply applied statistical analysis. Lightstep has built most of our powerful features on top of stats. Simple heuristics. If you look at what we're doing and what an AIOps tool is doing, they're basically the same. Looking at a lot of data and doing some math on it and figuring out, is this better or worse, or should I tell someone? That's simple. Do more of that. The second thing we need to remember is that computers aren't magic. We can create intelligent machines, but we can't really create wise ones, and there's a huge difference there, right? I can make a computer that can tell me, hey, I can give you, show me a picture and I can tell you if it's fruit salad. But it takes a machine with wisdom to understand that a tomato salad is not fruit salad, right? And that's how machine learning models work. They're regurgitating things that they already know and they need people to kind of help them along. There was, kind of this recent thing about a face depixelizer that is de-anonymizing people. And I think that's not really what it does, because it doesn't do that. It turns black people into white people, which is unfortunate for a lot of reasons due to training data. But ultimately, you can't, that's not how any of this works. This is not how any of this works. If you have a lossy algorithm applied to some piece of data, you cannot just ML your way back into full resolution. It's like if I took a puzzle, solved half of it, or solved the puzzle, threw away half the pieces at random, and then told the computer, hey, put the rest of the puzzle together. Unless it had seen that exact puzzle before, it could make a good approximation. It can make something that maybe looks right, but it's never going to be the same puzzle. The ML, the AI, all this stuff, it can't create something new. It can merely rearrange what's already been there. It's not magic. We have to be better about talking about this stuff and how we conceptualize it, because this has real world implications. This hurts people. There are machine learning and AI tools being used in communities around our country and around the world that are disproportionately harming black people, brown people, who have, ethnic minorities, whatever. We have people have gone to jail. There's 2 dudes in Detroit. Between when I made this deck and when I recording this talk, another person went to jail in Detroit based on a false identification from a machine learning computer vision algorithm. And outside the US, this is also a huge problem. In China, in the EU, this is not limited to just America. And a lot of the reason I think we do this, and the reason that people talk about it this way, is because we are promising the world and we are not saying stop. And it's time for us to say stop. Let's be realistic. Let's actually think about what's going on and be better about educating, both in a professional sense for what AI and ML can do, and also what it can't do. I think that AIOps fundamentally is this abandonment almost. We're abandoning our responsibility as technologists, and we're saying, yes, we just want to be little piggies, clocking in and punching numbers on a line. We just want to take all these hard decisions and put them on someone else's plate, or at least in this case, put them on the computer's plate. That's what Taylorism is, right? It's breaking down work into these, tiny pieces that are specialized and repetitive, and it sucks. Does this mean you shouldn't use it at all? I would say not necessarily, right? You shouldn't set the world on fire just because some things are bad, or even if there's a lot of things that are bad. AI, or machine learning specifically, is good if you have a homogeneous data set, right? It can go through there and it can do amazing things in terms of putting it back together and surfacing interesting data. You need to make sure that your algorithms are open and audible and observable, and that you understand what's going on, both in training and in, how it's coming to the conclusions that it's coming to. Finally, use computers, use machine learning to sort of surface these interesting hypotheses. And remember, it doesn't all come from machine learning. This is mostly just stats. But have the computer tell someone, hey, let me narrow the search space for you, right? Let me kind of cut down all the chaff. Because what we've been doing is we've been saying, hey, big AI company, here's $500,000, now solve a problem. And if you give someone a lot of money, then they'll find a problem to solve, right? They want to justify it. Ultimately, I think we should let computers do what the computers are good at, and then we should do what we're good at. And what we're good at is cooking. We're good at collaborating. We're good at talking. We're good at all these wonderful things. That's, when you think about, why do I use a rice cooker? It's not because I can't cook rice. I can cook rice. It's simple. Water, pot, boil, rice, go, done. But the time that I'm spending on cooking rice is time that I could be, doing something else in the kitchen. I could be helping my partner prepare a meal. And that's going to be more interesting to me, right? That's going to be something that I'm going to get more value out of, and that we're going to get more value out of, rather than me standing over a pot stirring it. So let the computer help, but make sure that you're not putting the computer in the lead. That's all I've got for you today. Thank you for your time, and I hope you have a great rest of the conference.